Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why some planets have no moons. Of the 8 major planets in our solar system, 2 orbit the Sun without any natural satellites. Mercury and Venus have no moons. This seems puzzling at first. Mars, smaller than either Mercury or Venus, has 2 small moons. Earth has 1 large moon. The giant planets beyond Mars have dozens or even hundreds of moons. Why would some planets capture or retain moons, while others remain moonless? The answer involves a complex interplay of gravitational dynamics, orbital mechanics, planetary formation history, and the specific environments in which these planets exist. The first factor to consider is proximity to the Sun. Mercury, the innermost planet, orbits at an average distance of only 58 million kilometers from the Sun. Venus orbits at 108 million kilometers. At these distances, the Sun's gravitational influence is overwhelming. For a moon to remain in a stable orbit around a planet, it must orbit within a region called the Hill sphere, the volume of space where the planet's gravity dominates over the Sun's gravity. The Hill sphere's size depends on the planet's mass and its distance from the Sun. The farther from the Sun, the larger the Hill sphere. The more massive the planet, the larger the Hill sphere. Mercury's Hill sphere extends only about 175,000 kilometers from the planet, less than half the distance from Earth to our Moon. Venus's Hill sphere is larger, extending about 1 million kilometers. But these regions are small compared to the Hill spheres of the outer planets. Earth's Hill sphere extends about 1.5 million kilometers. Jupiter's extends about 50 million kilometers. The small hill spheres around Mercury and Venus mean there's simply less space where a moon could maintain a stable orbit. But having a small hill sphere doesn't automatically prevent moon formation or capture. The real problem comes from tidal forces exerted by the Sun. Tidal forces arise because gravity weakens with distance, creating a differential pull across an extended object. The Sun's tidal forces on a potential moon of Mercury or Venus would be much stronger than the tidal forces experienced by moons of more distant planets, simply because these inner planets are so close to the Sun. These solar tides compete with the planet's own gravity for control of the moon's orbit. Over time, solar tidal perturbations can destabilize a moon's orbit, causing the orbit to become increasingly elliptical or inclined. Eventually, the moon might either crash into the planet, drift away into an independent orbit around the Sun, or get ejected from the system entirely. The closer the planet is to the Sun, the stronger these destabilizing effects become. There's a critical region around each planet, well inside the Hill sphere, where orbits can remain stable over billions of years despite solar perturbations. This region is typically only about 1/3 to 1/2 the radius of the Hill sphere. For Mercury, this stable region extends perhaps only 60,000 to 80,000 kilometers from the planet. For Venus, perhaps 300,000 to 500,000 kilometers. Any moon orbiting farther out would likely be stripped away by solar tides over geological time. But this raises another question. Why didn't small moons form or get captured in these inner stable regions? To understand this, we need to consider how moons form in the first place. There are 3 primary mechanisms. Co-formation, where the moon forms from the same disk of material as the planet. Capture, where the planet's gravity snares a passing object. And giant impact, where debris from a massive collision coalesces into a moon. The giant impact hypothesis explains Earth's moon. About 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact ejected enormous amounts of material into orbit around Earth, and this debris quickly coalesced into the Moon. This mechanism requires specific conditions, a large impactor at the right velocity and angle. Mercury and Venus likely experienced giant impacts during the chaotic early solar system, but any moons formed from such impacts would face additional challenges. Mercury's proximity to the Sun means that debris from an impact would orbit in an environment where solar tides are extremely strong. Material orbiting Mercury would experience differential forces from the Sun that could prevent it from coalescing into a moon or could destabilize any moon that did form. Additionally, Mercury's slow rotation, it rotates once every 59 Earth days, means it couldn't have transferred much angular momentum to a moon through tidal interactions, which helps stabilize moon orbits over time. Venus presents a different puzzle. It's larger than Mercury, more massive, and farther from the Sun, with a correspondingly larger hill sphere and stable region. Venus should be able to retain a moon more easily than Mercury, yet Venus is moonless. Several theories attempt to explain this anomaly, and the answer might involve Venus's unique rotation. Venus rotates incredibly slowly. One Venusian day lasts 243 Earth days, and it rotates backward relative to its orbital motion, a condition called retrograde rotation. This retrograde rotation is unusual and likely resulted from one or more giant impacts that altered Venus's spin. If Venus once had a moon formed from such an impact, the combination of Venus's slow retrograde rotation and solar tides could have caused the moon to spiral inward rather than outward. On Earth, tidal interactions with the moon cause the moon to gradually recede. It's moving away from Earth at about 3.8 centimeters per year. This happens because Earth's rotation is faster than the moon's orbital period, so tidal bulges on Earth are carried ahead of the Earth-Moon line, pulling the moon forward in its orbit and transferring angular momentum. For a moon orbiting retrograde Venus, or orbiting a very slowly rotating Venus, the tidal dynamics work differently. The tidal bulges would lag behind rather than lead, causing the moon to lose orbital energy and spiral inward toward the planet. Eventually, the moon would cross the Roche limit, the distance inside which tidal forces overcome the moon's self-gravity, and be torn apart. The fragments would either fall onto Venus or spread into a ring system that gradually decayed, with particles spiraling down to the planet's surface over millions of years. If Venus had a moon in the distant past, this mechanism could have destroyed it billions of years ago. Alex Alemi and David Stevenson proposed this scenario in 2006, suggesting that Venus's slow retrograde rotation would cause any moon to spiral inward and be destroyed within tens of millions of years. Their calculations showed that even a large moon, similar in size to Earth's moon, would meet this fate if Venus rotated slowly enough. The giant impact that created the moon might also have been responsible for slowing or reversing Venus's rotation, setting up the conditions for the moon's eventual destruction. Capture represents another moon formation mechanism, but it faces significant challenges. For a planet to capture a passing asteroid or other object, something must remove energy from the object's orbit during the close encounter. Otherwise, the object simply swings past the planet and continues on its way. Energy can be removed through atmospheric drag if the planet has a thick atmosphere, through gravitational interactions with existing moons in a three-body interaction, or through tidal forces if the encounter is extremely close. Mercury has essentially no atmosphere, so atmospheric capture is impossible. Venus has a thick atmosphere, but capturing an object large enough to be considered a moon rather than just a small asteroid would require the object to pass through the upper atmosphere at just the right velocity and angle, an unlikely scenario. Mars's two small moons, Phobos and Deimos, might be captured asteroids, but they're tiny. Phobos is only about 22 kilometers across and Deimos about 12 kilometers. Mars likely captured them during the early solar system when more debris was available and orbital dynamics were more chaotic. For Mercury and Venus, the combination of their locations in the inner solar system, where fewer large objects were available for capture, and the difficulty of the capture process itself, meant that gravitational capture of moons was unlikely. The inner solar system was largely cleared of debris early in solar system history, as objects either accreted into planets, fell into the Sun, or were ejected to the outer system through gravitational interactions with the growing planets. The composition and formation history of the inner planets also matters. Mercury, Venus, Earth, and Mars formed from the inner portion of the protoplanetary disk, where temperatures were too high for ice to condense. These planets formed primarily from rocky and metallic materials. The giant planets formed farther out, where ices could exist, providing more material for planet and moon formation. The abundance of material in the outer solar system, both for forming the planets themselves and for forming moons, was simply greater than in the inner solar system. The giant planets likely formed their large regular moons, the major satellites that orbit in the planet's equatorial plane, from circumplanetary disks, miniature versions of the protoplanetary disk that surrounded the young Sun. These disks contained enough material to form multiple large moons. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610, formed this way. Saturn's major moons, including Titan, formed similarly. The inner planets, with less mass and forming in a region with less available material, likely didn't have substantial circumplanetary disks, making it difficult to form moons through this mechanism. Exoplanet studies have revealed that moonless planets might be quite common. Many exoplanets discovered so far are hot Jupiters, gas giants orbiting extremely close to their host stars, often closer than Mercury orbits the Sun. These planets, despite being massive, likely have no moons because the extreme proximity to their stars creates even more severe tidal effects than Mercury experiences. Any moons would be quickly stripped away by stellar tides. Some hot Jupiters may have had moons when they formed farther from their stars, but lost them as the planets migrated inward to their current close-in orbits. Other exoplanets orbit in the habitable zones of their stars at distances where moons could potentially remain stable. Whether these planets have moons depends on their formation history, the availability of material for moon formation, and the dynamical environment in which they formed. Detecting exomoons, moons orbiting exoplanets, remains at the edge of current observational capabilities, though several candidates have been proposed. As detection techniques improve, we'll learn whether most planets have moons or whether moonless planets are actually the norm. The absence of moons around Mercury and Venus is not a deficiency, but rather a natural consequence of where these planets are located and how they formed. Their proximity to the Sun creates an environment where moons cannot easily form or survive over billions of years. Any moons that might have existed in the early solar system were likely destroyed by solar tides, spiraled into the planets due to tidal interactions with slowly rotating worlds, or were ejected from unstable orbits. The planets that do have moons, Earth, Mars, and especially the giant planets, possess them because they orbit farther from the Sun, where Hill spheres are larger, solar tides are weaker, and the environment is more conducive to moon formation and retention, showing that the presence or absence of moons depends not on the planet's inherent qualities, but on the orbital and environmental context in which the planet exists, making our own moon's existence not a given, but rather the result of a fortunate combination of location, timing, and the specific collision that created it billions of years ago. How black holes warp time itself. Time is not the constant, uniform flow that our everyday experience suggests. It can stretch, compress, and slow down depending on the gravitational environment you're in. Nowhere is this more extreme than near a black hole, where gravity becomes so intense that time itself warps in ways that challenge our intuition and transform our understanding of reality. Understanding how black holes affect time means grappling with one of the most profound insights of modern physics, that space and time are not separate, fixed stages on which events unfold, but rather a unified fabric that can be bent, twisted, and stretched by the presence of mass and energy. The foundation for understanding time dilation near black holes comes from Albert Einstein's general theory of relativity, published in 1915. Einstein proposed that what we perceive as gravity is actually the curvature of spacetime caused by mass and energy. Massive objects create depressions in the fabric of spacetime, much like a bowling ball placed on a stretched rubber sheet creates a depression that affects how nearby marbles roll. This curvature affects not just the paths that objects follow through space, but also the rate at which time passes. The basic principle is that time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been confirmed through countless experiments. Atomic clocks placed at different altitudes on Earth tick at measurably different rates. Clocks at sea level run slightly slower than clocks on mountaintops, because they're deeper in Earth's gravitational well. The difference is tiny, only nanoseconds per day, but it's real and measurable. GPS satellites must account for this effect. Without corrections for gravitational time dilation, GPS coordinates would drift by several kilometers per day. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers, one hovering far from a black hole in weak gravity, the other hovering closer to the black hole, where gravity is much stronger. If both observers synchronize their watches and then separate, the watch closer to the black hole will tick more slowly from the distant observer's perspective. This isn't an illusion or a malfunction of the watch. Time genuinely passes more slowly in the stronger gravitational field. The closer you get to a black hole, the more severe this effect becomes. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most counterintuitive aspects of black holes. If you were to watch someone fall toward a black hole while you remained safely far away, you would see something strange. As the falling person approached the event horizon, they would appear to slow down. Their movements would become sluggish, their signals would take longer to reach you, and their image would become increasingly red-shifted as the light they emit is stretched by the intense gravity. From your distant vantage point, the falling person would never quite seem to cross the event horizon. They would appear to freeze at the boundary, becoming dimmer and redder until they faded from view entirely. This isn't because they stopped falling. From their own perspective, they would cross the event horizon and continue falling inward in a finite amount of time, experiencing nothing unusual at that precise moment. The difference is entirely due to how time flows differently in different gravitational fields. This discrepancy between what the falling observer experiences and what the distant observer sees is one of the most mind-bending aspects of general relativity. Both perspectives are equally valid. The falling observer crosses the event horizon in, say, 10 seconds by their clock, but from the distant observer's perspective, watching that crossing would take infinite time. It would never be complete. This isn't a contradiction, but rather a demonstration that time is not absolute. Different observers in different gravitational fields experience time at different rates. The mathematics describing this time dilation near black holes was first worked out by Carl Schwarzschild in 1916, just months after Einstein published General Relativity. Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a non-rotating, spherically symmetric mass, what we now call a Schwarzschild black hole. His solution showed that time dilation increases as you approach the event horizon, located at what's now called the Schwarzschild radius, reaching infinite dilation exactly at the horizon. For a rotating black hole, described by the Kerr solution, found by Roy Kerr in 1963, the situation becomes even more complex. Rotation creates additional effects beyond simple time dilation. The black hole drags spacetime around with it in a process called frame dragging. Close to a rotating black hole, space itself is pulled around in the direction of rotation. You couldn't remain stationary even if you wanted to. You'd be forced to rotate with the spacetime itself. This creates regions like the ergosphere outside the event horizon, where frame dragging is so strong that everything must move in the direction of the black hole's rotation. The warping of time near black holes has practical implications for anything orbiting or falling toward them. Consider material in an accretion disk spiraling into a black hole. Material in the inner portions of the disk, closer to the black hole, experiences stronger time dilation than material farther out. From the perspective of an observer far from the black hole, processes in the inner disk appear to run in slow motion compared to processes in the outer disk. This affects how we observe black holes and interpret the light we receive from matter near them. Time dilation also affects the gravitational redshift of light, escaping from near a black hole. Light climbing out of a gravitational well loses energy, its wavelength stretching toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation. They're two aspects of the same phenomenon. A photon emitted from close to the event horizon will be dramatically redshifted by the time it reaches a distant observer. If the photon is emitted from the event horizon itself, it would be redshifted infinitely, its energy dropping to zero, another way of understanding why nothing can escape from beyond the horizon. Inside the event horizon, the warping of spacetime becomes even more extreme. In this region, the roles of space and time actually exchange in a sense. Outside the horizon, moving forward in time is inevitable. You cannot choose to move backward in time, but you can choose your direction in space. Inside the horizon, moving toward the singularity at the center becomes as inevitable as moving forward in time outside the horizon. All possible paths lead inward, and reaching the singularity becomes as unavoidable as reaching the next moment in time. The singularity at the center of a black hole represents a place where space-time curvature becomes infinite, and general relativity's equations break down. At the singularity, time itself becomes undefined in the classical sense. This suggests that general relativity is incomplete, that a theory of quantum gravity would be needed to properly describe what happens at and beyond the singularity. String theory, loop quantum gravity, and other approaches to quantum gravity propose different solutions to what occurs at this extreme limit, but none have been confirmed experimentally. Supermassive black holes at the centers of galaxies create fascinating time dilation effects on galactic scales. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, contains about 4 million solar masses. Stars orbiting close to this black hole experience measurable time dilation. A star in a close orbit around Sagittarius A star, coming within a few hundred times the black hole's event horizon radius, would experience time flowing noticeably slower than we experience it here on Earth, 26,000 light-years away. Precise measurements of these stars' orbits by Andrea Ghez and Reinhard Genzel, who shared the 2020 Nobel Prize in Physics for this work, have confirmed general relativity's predictions in this strong gravity regime. Time dilation near black holes has captured popular imagination, featuring prominently in science fiction. The film Interstellar depicted a planet orbiting close to a massive rotating black hole, where time dilation was so extreme that 1 hour on the planet's surface equaled 7 years of time passing elsewhere. While Hollywood took some liberties, the basic physics was sound. Physicist Kip Thorne served as scientific consultant and later published papers about the black hole physics portrayed in the film. Such extreme time dilation is theoretically possible near a rapidly rotating supermassive black hole. Binary black hole systems, where two black holes orbit each other before merging, create incredibly complex space-time geometries. Each black hole warps time in its vicinity, and the combined warping creates regions where time flows at different rates depending on your location relative to the two black holes. As the black holes spiral together and merge, events that produce the gravitational waves detected by LIGO and other observatories, the warping of spacetime becomes dynamical, with gravitational waves carrying information about how spacetime is oscillating and rippling during this violent event. The connection between time dilation and energy offers another perspective on these phenomena. According to general relativity, gravitational fields contain energy. A clock deep in a gravitational well, where time runs slowly, can be thought of as having less energy than a clock far from any gravitational source. The gravitational redshift of light, the loss of energy as light climbs out of a gravitational well, reflects this energy difference between different regions of curved spacetime. Black holes also raise profound questions about the nature of time itself. Some interpretations of quantum mechanics and general relativity suggest that time might not be fundamental, but rather an emergent property of more basic physical processes. Black holes, where classical notions of time break down at the singularity, might provide clues about the true nature of time. The information paradox, the question of what happens to information that falls into a black hole, connects to deep questions about time, entropy, and the quantum nature of spacetime. Hawking radiation, predicted by Stephen Hawking in 1974, introduces another connection between black holes and time. Quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate over extremely long timescales. This process involves virtual particle pairs appearing near the horizon, with one particle falling in while the other escapes. The evaporation means black holes have a finite lifetime, and it connects quantum mechanics, gravity, and thermodynamics in ways that hint at a deeper theory unifying these domains. The warping of time near black holes is not science fiction, but established physics, confirmed through observations and experiments. Every time LIGO detects gravitational waves from merging black holes, it's detecting ripples in spacetime that carry information about how dramatically spacetime, and therefore time itself, was warped during the merger. Every observation of matter orbiting near black holes, every measurement of gravitational redshift, every test of general relativity in strong gravitational fields, confirms that time is not absolute, but is woven into the fabric of spacetime, susceptible to warping and stretching by mass and energy, reaching its most extreme manifestation near black holes, where the flow of time slows to a crawl, and ultimately, at the event horizon, appears to stop entirely from the perspective of distant observers watching the inexorable pull of gravity on the fabric of reality itself. How galaxies live and die. Galaxies are not eternal, unchanging structures frozen in the void. They are dynamic systems that evolve over billions of years, passing through distinct phases from birth to maturity to eventual decline. Each galaxy follows a life story shaped by gravity, star formation, gas flows, and violent interactions with other galaxies, ultimately transforming from active star-forming systems into quiet collections of aging stars, or sometimes meeting more dramatic fates in collisions that tear them apart and rebuild them into something new. The birth of a galaxy begins in the early universe, just a few 100 million years after the Big Bang. At this time, the cosmos was filled with vast clouds of hydrogen and helium, distributed nearly uniformly, but with tiny variations in density imprinted during the first moments after the Big Bang. Dark matter, invisible but gravitationally powerful, began to collapse first into clumps and filaments, creating gravitational wells that attracted normal matter. Gas flowed along these dark matter filaments, accumulating in regions where the gravitational pull was strongest. These early accumulations of gas were turbulent, chaotic places. The gas was cold, collapsing under its own gravity into smaller and smaller clumps. Within these collapsing clouds, the first stars ignited, massive and brilliant, burning through their nuclear fuel in just a few million years before exploding as supernova. These explosions enriched the surrounding gas with heavier elements, carbon, oxygen, iron, and others, that hadn't existed in the primordial universe. More stars formed from this enriched gas, creating a positive feedback cycle where star formation bred more star formation. A young galaxy is a vigorous place, forming stars at prodigious rates. Gas continues to fall into the galaxy from the surrounding cosmic web, providing fresh fuel for star formation. These early galaxies are often irregular in shape, lacking the elegant spiral arms or smooth elliptical forms of mature galaxies. They're clumpy and asymmetric, filled with giant regions of intense star formation where thousands of stars are being born simultaneously. The massive stars in these regions produce copious ultraviolet radiation that ionizes the surrounding gas, creating glowing nebulae visible across vast distances. As a galaxy matures, it begins to develop structure. If it has significant angular momentum, inherited from the rotation of the gas cloud from which it formed, it settles into a rotating disk. Within this disk, density waves organize stars and gas into spiral arms, elegant patterns that rotate around the galactic center. Stars form preferentially in these spiral arms, where gas is compressed by the passing density wave. The galaxy takes on the classic spiral form we see in galaxies like our own Milky Way or the nearby Andromeda galaxy. The disk of a spiral galaxy contains young hot blue stars mixed with older, cooler yellow and red stars. Gas lanes trace the spiral arms, visible as dark patches where dust blocks light from stars behind. At the center lies the bulge, a roughly spherical concentration of older stars, and at the very heart of the bulge lurks a supermassive black hole, containing millions to billions of times the mass of the Sun. This black hole profoundly influences the galaxy's evolution, though in ways that are still not completely understood. Star formation in a mature galaxy is a self-regulating process. Gas collapses to form stars, but the stars themselves affect the gas around them. Massive stars produce powerful winds that push gas away. Supernova explosions inject tremendous energy into the interstellar medium, heating gas and driving it outward in expanding bubbles and shells. This feedback can temporarily suppress star formation in regions around young star clusters, giving the galaxy a breathing, pulsating quality where star formation surges and ebbs over millions of years. The supermassive black hole at a galaxy's center can dramatically affect its evolution. When gas falls toward the black hole, it forms an accretion disk, heating to millions of degrees and emitting intense radiation across the electromagnetic spectrum. This active galactic nucleus can outshine all the stars in the galaxy combined. The energy released can drive powerful winds and jets that blow gas out of the galaxy entirely, removing the raw material needed for star formation. Many galaxies go through active phases when their central black holes are feeding vigorously, then quiet phases when little material is falling inward and the black hole lies dormant. Galaxies don't evolve in isolation. They're part of a cosmic web, connected by filaments of dark matter and gas to other galaxies nearby. Smaller galaxies fall into larger ones, adding their stars and gas to the growing giant. The Milky Way has consumed dozens of smaller satellite galaxies over its history, and it will consume more in the future. Each merger adds complexity to the galaxy's structure, sometimes triggering bursts of star formation as gas clouds collide and compress, sometimes disrupting the orderly rotation of the disk and scattering stars into less organized orbits. Major mergers, when two galaxies of comparable size collide, are transformative events. The collision unfolds over hundreds of millions of years as the galaxy's gravitational fields interact. Stars almost never collide directly. The distances between stars are so vast that even in a galactic collision, stellar collisions are extraordinarily rare. But the gravitational interactions between the passing galaxies create tidal forces that stretch and distort each galaxy's structure. Long tidal tails of stars and gas stream away from the collision site, some eventually falling back into the merged system, others dispersed into intergalactic space. The gas in colliding galaxies does collide, directly and violently. Giant molecular clouds slam together at speeds of hundreds of kilometers per second, creating shockwaves that compress the gas and trigger intense bursts of star formation. These starburst galaxies can form stars at rates hundreds of times higher than normal galaxies, converting much of their gas into stars within just tens of millions of years. The newly formed massive stars live brief lives and explode as supernovae, creating a cascade of feedback that heats the remaining gas and can drive much of it out of the galaxy entirely. The end result of a major merger is typically an elliptical galaxy. The orderly rotation of the spiral disks is destroyed by the chaotic gravitational interactions of the merger. Stars end up on random orbits, creating a roughly spherical or elliptical distribution rather than a flat disk. Elliptical galaxies contain mostly old stars, appearing yellowish or reddish because they lack the young blue stars that make spiral galaxies appear white or blue. They have little gas left for star formation, having either converted most of their gas into stars during the merger or expelled it through feedback from star formation and active galactic nuclei. Elliptical galaxies represent a kind of middle age or retirement for galaxies. They're massive, sometimes containing trillions of stars, but they're largely quiescent, forming few new stars. The stars within them are aging, slowly converting hydrogen to helium in their cores, gradually dimming as they exhaust their fuel. Over hundreds of billions of years, these stars will die one by one. Low-mass stars will swell into red giants, then shed their outer layers as planetary nebulae, leaving behind white dwarf remnants. Higher-mass stars will explode as supernova, leaving neutron stars, or black holes. As stars die, they return some of their material to the interstellar medium, but much of their mass remains locked in stellar remnants. The galaxy's gas supply dwindles, and with no new gas falling in from outside, star formation gradually ceases. The galaxy grows dimmer as its most luminous stars die and are not replaced. Eventually, in the far future, such a galaxy would consist primarily of white dwarfs, neutron stars, and black holes, the dead remnants of stars that once shone brightly. Some galaxies meet more dramatic ends. In dense galaxy clusters, high-speed collisions and gravitational interactions can tear galaxies apart. Ram pressure stripping occurs when a galaxy moves through the hot intracluster gas that fills the space between galaxies in a cluster. This hot gas, though tenuous, exerts pressure on the cold gas in the moving galaxy, stripping it away like wind pulling leaves from a tree. The galaxy is left with no gas for star formation, rapidly aging as its existing stars evolve and die without being replaced. Galaxies can also be tidally disrupted by close passes to much more massive galaxies. The tidal forces, the difference in gravitational pull between the near and far sides of the smaller galaxy, can be strong enough to overcome the galaxy's self-gravity, pulling it apart into streams of stars that wrap around the larger galaxy. The Milky Way is currently in the process of tidally disrupting the Sagittarius dwarf elliptical galaxy, a small galaxy that passed too close and is now being stretched into a stream of stars encircling our galaxy. In the very long term, over timescales of trillions of years, galaxies face a dark future. The expansion of the universe, driven by dark energy, is accelerating. Galaxy clusters will remain gravitationally bound, but individual clusters will become increasingly isolated from each other as the space between them grows. Within each cluster, galaxies will gradually merge, forming ever larger elliptical galaxies. Eventually, each cluster will merge into a single giant elliptical galaxy containing all the matter that was once in dozens or hundreds of separate galaxies. Even these ultimate galaxies will fade. Star formation will cease entirely as all available gas is either converted into stars or expelled from galaxies. The remaining stars will age and die. White dwarfs will cool, becoming black dwarfs, cold, dark stellar remnants that no longer emit visible light. Neutron stars will radiate away their heat over inconceivable timescales. Black holes will slowly evaporate through Hawking radiation, though this process takes vastly longer than the current age of the universe. 10 to the power of 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 10 to 100th power years for a solar mass black hole, far longer for the supermassive black holes at galaxy centers. The life cycle of galaxies is intimately connected to the larger evolution of the universe itself. In the early universe, galaxies formed rapidly and evolved quickly, building up their stellar populations and establishing their structures. In the current era, galaxies continue to form stars but more sedately, and many have settled into mature configurations. In the far future, galaxy formation will cease as the expanding universe spreads matter too thinly for new gravitational collapses to occur. The galaxies that exist will gradually fade as their stars die and are not replaced. But this distant future is trillions of years away. For now, and for the foreseeable future, galaxies remain vibrant systems. Star formation continues, though at lower rates than in the past. Galaxies merge and interact, transforming themselves in violent collisions that reshape their structures. New observations reveal galaxies at ever greater distances, showing us how they looked when the universe was young, allowing us to piece together the story of how galaxies live and die, how they transform over cosmic time, and how the universe itself evolves through the changes that galaxies undergo as they pass through their long but finite lifespans. How planets form from dust. In the beginning, there were no planets. No Earth, no Jupiter, no rocky worlds or gas giants, just vast clouds of gas and dust drifting through the galaxy. Yet from these diffuse, seemingly formless clouds, gravity and physics conspired to build the solid worlds we see today. Understanding how planets form from dust means understanding one of nature's most remarkable construction projects, a process that transforms microscopic particles floating in space into spheres thousands of miles across, complete with cores, mantles, atmospheres, and sometimes even moons. The story begins with a molecular cloud, a cold, dark region of space, filled primarily with hydrogen and helium gas left over from the Big Bang, mixed with about 1% heavier elements and dust particles created in previous generations of stars. These dust grains are tiny, typically only a fraction of a micrometer across, smaller than bacteria. They're composed of silicates, rocky minerals similar to sand, and sometimes ices of water, carbon dioxide, or methane, depending on the temperature of the cloud. Something disturbs the cloud. Perhaps a nearby star explodes as a supernova, sending a shockwave rippling through space. Perhaps the cloud passes through a spiral arm of the galaxy where gas is compressed. Whatever the trigger, a region of the cloud begins to collapse under its own gravity. As it collapses, it spins faster due to conservation of angular momentum. The same principle that makes a figure skater spin faster when pulling their arms inward. The collapsing cloud flattens into a disk, a swirling pancake of gas and dust with a growing concentration of mass at the center. This is a protoplanetary disk, and it's where planets will form. The center grows hotter and denser as material falls inward, eventually becoming a protostar that will ignite nuclear fusion and become a star. But the disk surrounding the star contains enough material to build an entire family of planets. In the disk, dust particles drift through the gas, occasionally bumping into each other. When they collide gently, they can stick together. The sticking happens through several mechanisms. Sometimes electrostatic forces, essentially static electricity, cause particles to cling to each other. Sometimes molecular forces, similar to the forces that make wet sand stick together, bind the particles. Ice coatings on particles in the colder outer regions of the disk act like glue, making particles particularly sticky. These gentle collisions build larger particles. A dust grain collides with another, and they stick, forming a slightly larger grain. This larger grain has a bigger cross-section, making it more likely to encounter and stick to other grains. Slowly, grain by grain, the particles grow from microscopic dust into pebbles, then into rocks, then into boulders. This process, called accretion, is slow at first but accelerates as particles grow larger. The growing clumps begin to settle toward the midplane of the disk. the thin central plane where the density is highest. Larger particles settle faster than smaller ones because they're less buffeted by gas turbulence. The midplane becomes a dense layer of solid material embedded in the gas disk, creating favourable conditions for further growth. Particles collide more frequently in this dense environment, accelerating the growth process. When the solid objects reach sizes of about a kilometre across, they're called planetesimals. These are the building blocks of planets, and reaching this size represents a critical milestone. Objects this large have enough gravity to begin attracting nearby material rather than relying solely on chance collisions. Their gravity pulls in smaller rocks and dust, causing them to grow faster. The biggest planetesimals grow the fastest because their stronger gravity allows them to clear out larger regions of the disk, creating what astronomers call runaway growth. The protoplanetary disk is a chaotic place. Planetesimals don't just grow peacefully, they also collide with each other. Some collisions are gentle enough that the objects merge, creating larger bodies. But other collisions are violent, shattering one or both objects into fragments. Whether a collision leads to growth or destruction depends on the relative velocities. Slow collisions, at a few meters per second, tend to result in sticking and growth. Fast collisions at kilometers per second tend to be destructive. Over time, certain planetesimals become dominant, growing larger than their neighbours. These become planetary embryos, objects roughly the size of our Moon or Mars, hundreds to thousands of kilometers across. The largest embryos in each region of the disk sweep up most of the available material in their vicinity, clearing out their orbital zones. When two similarly sized embryos eventually collide, the impact can be cataclysmic, melting both objects and creating a larger planet from the merged material. The composition of forming planets depends on their distance from the star. Close to the star, temperatures are high, hot enough that volatile materials like water, methane, and ammonia can't condense into solid form. Only materials with high melting points, metals and rocky minerals, can exist as solids. This is why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are rocky worlds made of iron and silicates. Farther from the star, beyond a boundary called the snow line or ice line, temperatures are cold enough for water to freeze into ice. This fundamentally changes planet formation. Because ice is abundant, there's simply more solid material available when you include ice along with rock and metal. The snow line in our solar system was located somewhere around where the asteroid belt is today, between Mars and Jupiter. Beyond the snow line, planetary embryos could grow much larger because more solid material was available. When an embryo grew to roughly 10 times Earth's mass, something dramatic happened. Its gravity became strong enough to capture gas directly from the surrounding disk. Hydrogen and helium, the most abundant elements in the disk, began falling onto the growing planet. Once this process started, it ran away rapidly. The planet's gravity pulled in more gas, which made it more massive, which increased its gravity, which allowed it to pull in even more gas. This runaway gas accretion created the gas giant planets, Jupiter and Saturn, in our solar system. These worlds are mostly hydrogen and helium, like miniature stars, with relatively small rocky and icy cores buried beneath thousands of kilometers of gas. Jupiter grew so large and so quickly that it dominated its region of the solar system, its powerful gravity stirring up the asteroid belt and preventing the material there from ever forming a planet. Uranus and Neptune, the ice giants, also formed beyond the snow line, but grew more slowly. They captured some gas from the disk, but not as much as Jupiter and Saturn, possibly because the gas in their region was less dense or because the disk dispersed before they could grow large enough to undergo runaway gas accretion. These planets are dominated by water, methane, and ammonia ices, rather than hydrogen and helium gas. The protoplanetary disk doesn't last forever. The young star at the center begins generating powerful stellar winds and intense radiation. Over a few million years, this wind sweeps away the remaining gas in the disk, ending the era of planet formation from gas accretion. Any planets that hadn't finished growing could no longer capture gas from the disk. This probably explains why Mars is so small. It formed in a region where less material was available, and the gas dispersed before it could grow much larger. Even after the gas disk disperses, planet formation continues through collisions between the remaining planetesimals and planetary embryos. This era, called the late heavy bombardment or giant impact phase, was violent. Computer simulations suggest that the inner solar system initially formed several more planetary embryos than the 4 terrestrial planets we see today. These embryos had chaotic, crossing orbits, and they repeatedly collided over tens of millions of years. Eventually, through this sequence of giant impacts, the embryos merged into the 4 stable planets, Mercury, Venus, Earth, and Mars, we observe today. Earth's moon likely formed during one of these giant impacts. About 4.5 billion years ago, a Mars-sized object struck the young Earth at an oblique angle. The impact vaporized both the impactor's outer layers and a large portion of Earth's mantle, ejecting an enormous amount of material into orbit around Earth. This material, a mixture of vaporized rock and molten droplets, quickly coalesced into the Moon. The Moon's composition, which closely matches Earth's mantle but lacks iron from Earth's core, supports this giant impact origin. The timing of planet formation varies. In our solar system, Jupiter formed within a few million years, fast enough to capture gas before the disk dispersed. The terrestrial planets took longer, perhaps tens of millions of years to reach their final sizes. The final giant impacts on Earth, including the moon-forming impact, occurred somewhere around 50 to 100 million years after the disk first started collapsing. This might seem long, but it's less than 1% of Earth's current age. Planet formation is remarkably quick on astronomical timescales. Not all the material in the protoplanetary disk becomes part of planets. Some planetesimals survive in stable regions where planets didn't form. The asteroid belt contains remnants of planetesimals that never accreted into a planet, stirred up and prevented from merging by Jupiter's gravitational influence. The Kuiper belt beyond Neptune and the more distant Oort cloud contain frozen planetesimals preserved from the solar system's formation, rich in ices that couldn't exist in the warmer inner regions. Observations of protoplanetary disks around young stars show this process happening in real time. The Atacama Large Millimeter Array in Chile has captured stunning images of disks with gaps and rings, structures created by forming planets as they clear out their orbital zones. Some disks show spiral patterns caused by gravitational perturbations from massive planets still embedded in the disk. These observations confirm that planet formation is common and that the process we see in our solar system occurs around most stars. Planet formation doesn't always produce systems like ours. Exoplanet discoveries have revealed hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. These planets must have formed farther out beyond the snow line, where ice could exist, then migrated inward through gravitational interactions with the disk or with other planets. Some planetary systems are extremely compact, with multiple planets orbiting closer to their star than Mercury. Others have planets on highly elliptical orbits, unlike the nearly circular orbits in our solar system. From microscopic dust grains to planet-sized worlds represents a journey across more than 10 orders of magnitude in size, a factor of tens of billions. The process transforms diffuse material spread across millions of miles into concentrated spheres where gravity compresses matter so intensely that planetary interiors melt and differentiate into layers, where atmospheres form and weather patterns emerge, and where, at least on one planet we know of, conditions become suitable for life to arise. All of this complexity, all of this structure, emerges from nothing more than dust, gas, gravity, and time, following the laws of physics that govern how matter behaves when concentrated by the inexorable pull of gravity in the rotating disk around a young star. How we find planets around other stars. For most of human history, planets were only known to exist in our own solar system. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye, and with telescopes came the discoveries of Uranus and Neptune. But beyond our solar system, despite billions upon billions of stars filling the galaxy, no one had ever confirmed the existence of even a single planet orbiting another star. The problem wasn't that exoplanets, planets around other stars, didn't exist. The problem was that they're extraordinarily difficult to detect. A planet is tiny compared to its star, produces no light of its own, and sits right next to a brilliant star that outshines it completely. Trying to see a planet next to its star is like trying to spot a firefly hovering next to a searchlight from hundreds of miles away. The first confirmed exoplanet around a sun-like star was discovered in 1995 by Michel Mayor and Didier Queloz, who shared the Nobel Prize in Physics in 2019 for this groundbreaking work. They didn't actually see the planet. Instead, they detected its presence indirectly by observing how it affected its parent star. This indirect approach has proven to be the key to finding exoplanets, and astronomers have developed several clever techniques that reveal planets without ever actually imaging them directly. The method Mayor and Queloz used is called the radial velocity technique, sometimes known as the Doppler wobble method. The basic principle relies on the fact that a planet doesn't simply orbit its star. Rather, both the planet and the star orbit their common center of mass. Imagine two ice skaters holding hands and spinning around. If one skater is much heavier than the other, the heavy skater barely moves, while the light skater whips around in a large circle. But the heavy skater does move slightly, wobbling around their common center as they spin. The same happens with stars and planets. Jupiter, the most massive planet in our solar system, causes the Sun to wobble slightly as both orbit their common center of mass. The Sun's wobble is small. It shifts back and forth by only about 13 meters per second, roughly the speed of a bicycle. But this wobble is detectable. As the star moves toward Earth, its light gets slightly blue shifted, compressed to shorter wavelengths. As it moves away, the light gets red shifted, stretched to longer wavelengths. By measuring these tiny shifts in the star's spectrum with extremely precise instruments, astronomers can detect the wobble and infer that a planet must be causing it. The planet Mayor and Queloz discovered, orbiting a star called 51 Pegasi, created a much larger wobble than Jupiter creates in our Sun, because this planet is both massive and very close to its star. It completes an orbit in just over 4 days, compared to Jupiter's 12-year orbit. The close proximity and short period make the wobble more pronounced and easier to detect. This planet, later named Dimidium, shocked astronomers because it's a gas giant similar to Jupiter, but orbiting closer to its star than Mercury orbits our Sun. Before this discovery, most astronomers assumed that giant planets could only form far from their stars, where temperatures were cold enough for ice to exist. The discovery of hot Jupiters revolutionized our understanding of how planetary systems form and evolve. The radial velocity method works best for finding massive planets close to their stars because these create the largest wobbles. Small planets like Earth create wobbles so tiny that they're difficult to detect even with the best current instruments. A planet similar to Earth orbiting a Sun-like star at Earth's distance would cause a wobble of less than 1 meter per second, slower than walking pace. Detecting such minute velocity changes requires incredibly stable spectrographs and careful corrections for other sources of stellar variability, like star spots and convection in the star's atmosphere. The second major technique for finding exoplanets is the transit method, which has discovered more exoplanets than any other technique. A transit occurs when a planet passes directly in front of its star, as seen from Earth, blocking a tiny fraction of the star's light. For a Jupiter-sized planet transiting a Sun-like star, the star's brightness drops by about 1%. A small change, but definitely measurable with precise photometry. For an Earth-sized planet, the drop is much smaller, only about 1/100th of 1%, but still detectable with sufficiently sensitive instruments. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to detect transits. Kepler monitored the brightness of more than 150,000 stars continuously for over 4 years, searching for the telltale dips in brightness that indicates a planet passing in front of its star. The mission was spectacularly successful, discovering thousands of exoplanets and showing that planets are common. Most stars have at least one planet, and many have multiple planets. Transit observations provide information that radial velocity measurements cannot. The depth of the transit, how much the star's brightness decreases, reveals the planet's size. A bigger planet blocks more light, creating a deeper transit. The duration of the transit reveals information about the planet's orbital distance and the star's size. By combining transit observations with radial velocity measurements, astronomers can determine both the planet's size and its mass, which allows them to calculate its density and infer what it might be made of. A low-density planet is probably a gas giant like Jupiter. A high-density planet is likely rocky like Earth. A medium density might indicate a water world or a planet with a thick atmosphere. The transit method has limitations. It only works for planets whose orbits happen to be aligned edge-on from Earth's perspective. If a planetary system is tilted so that planets pass above or below the star rather than directly in front of it, no transits occur, and the planets remain undetectable by this method. Statistically, only a small fraction of planets are oriented correctly for transits to be visible from Earth. For a planet at Earth's distance from a Sun-like star, the probability of correct alignment is less than 1%. Despite this limitation, Kepler's strategy of monitoring thousands of stars simultaneously meant that even with low individual probabilities, many planets were discovered. Direct imaging represents the most straightforward approach, actually taking a picture of the planet next to its star, but it's also the most technically challenging. The problem is the enormous brightness difference. A Sun-like star is typically 10 billion times brighter than a Jupiter-like planet at visible wavelengths, and the planet sits right next to the star in the sky. Special techniques are required to block the star's light and reveal the faint planet. Coronagraphs, which create an artificial eclipse by placing a mask over the star, and star shades, which fly separately from the telescope and block the star's light before it enters the telescope, both enable direct imaging. Direct imaging works best for young, massive planets that are far from their stars. Young planets are still hot from their formation, glowing brightly in infrared light, making the contrast ratio more favorable. Planets farther from their stars are more separated in angle, making them easier to distinguish from the star's glare. Several dozen planets have been directly imaged, mostly young gas giants orbiting at large distances from their stars. These planets appear as faint dots of light in images taken with large, ground-based telescopes equipped with adaptive optics systems that correct for atmospheric blurring. Gravitational microlensing provides another method for detecting exoplanets, particularly useful for finding planets at large distances from Earth and planets far from their host stars. The technique relies on general relativity. When one star passes almost directly in front of a more distant background star from Earth's perspective, the foreground star's gravity acts as a lens, bending and focusing the background star's light. This creates a temporary brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence. Microlensing events are rare and unpredictable. You can't choose to observe a particular star and wait for a microlensing event. Instead, astronomers monitor millions of stars in dense stellar regions, like the galactic bulge, waiting for events to occur. When an event happens, it's unique. The same foreground and background star will never align again in human timescales. This makes follow-up observations challenging, but the method has discovered several dozen planets and is particularly good at finding planets in the outer reaches of planetary systems where other methods struggle. Astrometry measures the precise position of a star in the sky over time. If a planet is present, the star wobbles back and forth on the sky, shifting position slightly as both star and planet orbit their common center of mass. This is similar to the radial velocity method, but measures the wobble in position rather than in velocity. The wobble is extremely small. For Jupiter orbiting the Sun, as seen from a distance of 10 light-years, the wobble would be about half a millisecond, roughly equivalent to measuring the width of a human hair from a distance of 200 miles. The European Space Agency's Gaia mission, launched in 2013, is measuring the positions of over 1 billion stars with unprecedented precision, and it's beginning to detect the astrometric wobbles caused by giant planets. As Gaia continues its mission and accumulates more data, it will discover planets through astrometry and provide three-dimensional orbital information for many planets discovered by other methods. Each detection method has biases. It favors finding certain types of planets over others. Radial velocity finds massive planets close to their stars. Transits find planets of all masses, but only those aligned edge-on. Direct imaging finds young massive planets far from their stars. Microlensing finds planets at all distances but works best for planets far from their stars. By using multiple methods, astronomers build a more complete picture of the diversity of planetary systems. The combination of techniques has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury. Super-Earths, planets larger than Earth but smaller than Neptune, appear to be extremely common, yet don't exist in our solar system. Some systems have planets in extremely compact orbits, with multiple planets packed closer to their star than Mercury is to our Sun. Other systems have planets on highly eccentric orbits, stretching from close in to far out in elongated ellipses. Some planets orbit binary stars, experiencing sunsets with two suns like Luke Skywalker's home planet Tatooine in Star Wars. The atmospheres of exoplanets can be studied through transit spectroscopy. When a planet transits its star, some starlight filters through the planet's atmosphere on its way to Earth. Different molecules in the atmosphere absorb light at specific wavelengths, creating an absorption spectrum that reveals the atmospheric composition. Astronomers have detected water vapor, methane, carbon dioxide, and other molecules in exoplanet atmospheres. The James Webb Space Telescope, launched in 2021, is revolutionizing this field with its ability to detect even fainter spectral signatures and characterize the atmospheres of smaller, potentially habitable planets. The search for Earth-like planets in habitable zones, the region around a star where temperatures allow liquid water to exist on a planet's surface, drives much exoplanet research. Kepler discovered several candidates, including Kepler 452b, a planet slightly larger than Earth orbiting a Sun-like star at a distance where temperatures might support liquid water. Whether any of these planets actually harbour life remains unknown, but the discovery that Earth-sized planets in habitable zones exist at all is profound. We're no longer wondering whether such planets exist, but rather whether any of them host life. Future missions will improve our ability to find and characterize Earth-like planets. The Nancy Grace Roman Space Telescope will use microlensing and direct imaging to find planets. Ground-based extremely large telescopes currently under construction will directly image planets and study their atmospheres in detail. Proposed missions like the Habitable Worlds Observatory aim to directly image dozens of Earth-like planets and search their atmospheres for biosignatures, gases like oxygen and methane that might indicate the presence of life. In less than 3 decades, exoplanet science has progressed from the first tentative discovery to finding thousands of planets, characterizing their properties, studying their atmospheres, and identifying candidates that might harbor life. The methods astronomers developed to overcome the challenge of finding tiny, faint planets next to brilliant stars have succeeded beyond initial expectations, revealing that planets are not rare accidents but common outcomes of star formation. That our solar system is just one example among billions of planetary systems filling the galaxy, and that the question of whether we're alone in the universe might finally be answerable through observations of the atmospheres of distant worlds orbiting alien suns. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where 2 lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When 2 asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a 3-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This 3-body capture was more common in the early solar system when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometre and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbits would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When 2 asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into 2 or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into 1 or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around 1 rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Chiron system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid-moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common center of mass. The asteroid Sylvia, about 260 kilometers in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometers from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometers, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometer-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How fast you'd need to go to leave a planet. Every object massive enough to have significant gravity holds onto anything near its surface. A ball thrown upward eventually falls back down. A bird must constantly flap its wings to stay aloft. Even the fastest jet aircraft cannot fly into space. Eventually it runs out of altitude and must descend. To truly leave a planet, to escape its gravitational grip entirely and coast into space without using any more fuel, you must reach a specific speed called escape velocity. This critical speed depends on the planet's mass and size, and understanding it reveals why launching rockets is so difficult, why some worlds can hold atmospheres while others cannot, and why the smallest push can send an astronaut drifting away from an asteroid while escaping Earth requires enormous rockets burning millions of pounds of fuel. Escape velocity is not about reaching a particular altitude or getting above the atmosphere. It's about speed, specifically moving fast enough that your kinetic energy equals or exceeds the gravitational potential energy binding you to the planet. If you launch something straight up at exactly escape velocity, it will climb higher and higher, slowing down continuously as gravity pulls it back, but never quite stopping. It will coast to infinite distance, arriving there with zero velocity, having converted all its initial kinetic energy into potential energy. Launch at any speed less than escape velocity, and gravity eventually wins, pulling the object back down. For Earth, escape velocity at the surface is about 11 kilometers per second, roughly 40,000 kilometers per hour, or about 25,000 miles per hour. This is more than 30 times faster than a typical passenger jet flies. To reach this speed, starting from rest requires enormous amounts of energy, which is why rockets are so large and burn so much fuel. The Saturn V rocket that launched Apollo missions to the Moon stood over 100 meters tall and weighed more than 2,000 tons at launch. But only about 50 tons of that mass, less than 3%, was the actual Apollo spacecraft and crew. Everything else was fuel and engines needed to accelerate that relatively small payload to the speeds necessary for spaceflight. Escape velocity depends on two factors: the planet's mass and its radius. More massive planets have higher escape velocities because stronger gravity pulls harder, requiring more speed to escape. Larger planets, meaning planets with larger radii, have lower escape velocities at their surfaces because you start farther from the center of mass where gravity is weaker. Earth is more massive than Mars, but also larger, and the combination means Earth's escape velocity is about 4.5 kilometers per second, higher than Mars's escape velocity of roughly 5 kilometers per second. This makes Mars somewhat easier to launch from than Earth. A rocket leaving Mars needs to reach only about half the speed required to leave Earth, which translates to roughly 1/4 the energy. Energy requirements scaled with the square of velocity. Mars's thinner atmosphere also helps, creating less air resistance during ascent. These factors make Mars an attractive location for future space missions that might launch from the surface to explore the outer solar system or return to Earth. The Moon, much smaller and less massive than Earth, has an escape velocity of only about 2.5 kilometers per second, less than 1/4 Earth's escape velocity. This made the Apollo lunar module's ascent from the Moon's surface relatively straightforward compared to launching from Earth. The ascent stage needed far less fuel and could use a much smaller engine. The low escape velocity also meant that the lunar module could take off without the massive multi-stage rockets required for Earth launch, using a single engine to reach lunar orbit directly. Jupiter, the most massive planet in our solar system, has an escape velocity from its cloud tops of about 60 kilometers per second, more than 5 times Earth's escape velocity. Launching from Jupiter, if there were a solid surface to launch from, would require vastly more energy than launching from Earth. Any spacecraft falling into Jupiter's atmosphere would need extraordinary speeds to escape again, which is why missions to Jupiter use gravity assists from other planets to gain speed rather than attempting to enter and exit Jupiter's deep gravity well. The concept of escape velocity explains why planets can hold atmospheres, while asteroids and comets cannot. Gas molecules in an atmosphere move at speeds related to temperature. Hotter gases move faster. For an atmosphere to remain bound to a body over billions of years, the typical speed of atmospheric molecules must be significantly lower than escape velocity. If molecules regularly reach speeds close to or exceeding escape velocity through random thermal motion, they leak away into space. Earth's atmosphere consists primarily of nitrogen and oxygen molecules that move at average speeds of a few hundred meters per second at normal temperatures, well below escape velocity. The lightest element, hydrogen, moves much faster at the same temperature because lighter molecules move faster for a given thermal energy. Hydrogen molecules at Earth's atmospheric temperature move at average speeds around 2 kilometers per second, which is still well below escape velocity, but close enough that over billions of years, Earth has lost most of its primordial hydrogen. The Moon's escape velocity is low enough that essentially no gas can remain in a lunar atmosphere. Any molecules would need to be extremely cold to have velocities below escape velocity, but solar heating warms the lunar surface during the long lunar day, giving molecules enough energy to escape. This is why the Moon has no atmosphere. Its weak gravity cannot hold even the lightest gases against thermal evaporation. Mars, with escape velocity between the Moon's and Earth's, represents an intermediate case. Mars can hold heavier molecules, like carbon dioxide in its atmosphere, but it loses lighter molecules more easily. Mars also lacks a strong magnetic field to protect its atmosphere from the solar wind, the stream of charged particles from the Sun. Over billions of years, the solar wind has stripped away most of Mars's original atmosphere, leaving the thin atmosphere we observe today. Escape velocity decreases with altitude. At the surface, you need to reach Earth's full escape velocity of 11 kilometers per second. But at the altitude where the International Space Station orbits, about 400 kilometers up, escape velocity is slightly less, around 10.9 kilometers per second. The difference is small because 400 kilometers is not much compared to Earth's radius of about 6,400 kilometers. But at lunar distance, about 380,000 kilometers, escape velocity from Earth has dropped to only about 1 kilometer per second. Apollo spacecraft needed to reach only this lower speed to escape Earth's gravity after coasting most of the way to the Moon. Escape velocity is the same in all directions. You could launch straight, up, horizontally, or at any angle, and you'd need the same speed to escape. The direction doesn't matter for escape, only the speed. However, in practice, rockets don't launch straight up. They curve their trajectory to gain horizontal velocity as well as altitude, because horizontal velocity is what's needed for orbit. Reaching escape velocity while moving horizontally means you escape while also having momentum that carries you away from the planet, rather than climbing straight up until you barely escape with zero velocity. Black holes represent the extreme case of escape velocity. At the event horizon, the boundary of a black hole, escape velocity equals the speed of light. Nothing can move faster than light, so nothing can escape from within the event horizon. This is what makes a black hole black. Not even light can escape once it crosses this boundary. For a black hole with a few times the Sun's mass, the event horizon has a radius of only about 10 kilometers. The extreme compression of mass into such a small radius creates escape velocities that reach and exceed the cosmic speed limit. Interestingly, you don't have to reach escape velocity to get into space. Rockets reaching orbit around Earth need to achieve only about 8 kilometers per second at orbital altitude, less than escape velocity. Orbital velocity is the speed at which your sideways motion exactly balances gravitational pull, so you continuously fall around the planet rather than falling back to it. This is easier to achieve than escape velocity, which is why orbital missions are more common than interplanetary missions. The Space Shuttle, for example, accelerated to about 8 kilometers per second to reach low Earth orbit, then used additional fuel to accelerate to higher speeds only when needed for missions to higher orbits or to the International Space Station. Missions leaving Earth orbit for the Moon, Mars, or other destinations required additional speed beyond orbital velocity to reach escape velocity and break free of Earth's gravity. Understanding escape velocity also explains how gravity assists work. When a spacecraft flies past a planet on a carefully calculated trajectory, it can gain speed by essentially stealing a tiny amount of the planet's orbital momentum. From the spacecraft's perspective, it falls toward the planet, swings around it, and flies away. If the trajectory is chosen correctly, the spacecraft leaves moving faster relative to the Sun than it arrived, having been accelerated by the planet's gravity without burning any fuel. The Voyager spacecraft used multiple gravity assists from Jupiter and Saturn to reach speeds high enough to eventually escape the solar system entirely, crossing into interstellar space decades after launch. Calculating how fast you'd need to go to leave a planet comes down to a simple formula involving the planet's mass and radius, derived from Newton's law of universal gravitation. The energy required to escape grows with planetary mass and shrinks with planetary radius, creating the variety of escape velocities we observe throughout the solar system. From tiny asteroids where you could literally jump into space if you weren't careful, to massive Jupiter where even the most powerful rockets would struggle to escape, the speed required to leave a world tells us about that world's fundamental properties and shapes everything from how we design spacecraft to which worlds can hold atmospheres, determining the accessibility of each destination in our cosmic neighborhood and beyond. How life could survive on rogue planets. Most planets orbit stars, bathed in starlight that provides warmth and energy for any life that might evolve. But scattered throughout the galaxy are worlds that wander alone, through the darkness of interstellar space. Rogue planets, ejected from their birth solar systems through gravitational interactions, or perhaps forming in isolation, drifting for billions of years without a sun to orbit. These orphaned worlds seem like the least hospitable places imaginable for life. Cut off from starlight, they receive no external heat source, no energy for photosynthesis, no warming to maintain liquid water on their surfaces. Yet despite these apparently insurmountable obstacles, life might still find ways to survive on rogue planets, drawing on internal heat sources, subsurface environments, and the remarkable adaptability that evolution has demonstrated countless times on Earth when organisms colonize seemingly impossible habitats. The key to habitability on rogue planets is internal heat. Unlike stars, which generate heat through nuclear fusion, rogue planets must rely on residual heat from formation and ongoing heat from radioactive decay of elements in their interiors. When planets form, the process of accretion, countless collisions between smaller bodies that gradually build up the planet, converts kinetic energy into heat. Additionally, gravitational compression, as material piles up, releases energy that heats the planet's interior. A newly formed planet is molten or partially molten, taking millions to billions of years to cool. This primordial heat, combined with heat from radioactive decay of uranium, thorium, potassium, and other radioactive isotopes in the planet's rocks, keeps planetary interiors warm for billions of years. Earth itself generates about 47 terawatts of internal heat, roughly equal to 10,000 large power plants operating continuously. Most of this heat comes from radioactive decay, with some contribution from residual primordial heat and from crystallization of Earth's molten iron core. This internal heat drives plate tectonics, powers volcanic activity, and maintains Earth's magnetic field. A rogue planet of similar size and composition would generate similar amounts of internal heat, regardless of whether it orbits a star or drifts through interstellar space. The challenge is keeping that heat trapped. Without an atmosphere, heat would radiate directly into space, and the planet's surface would quickly reach temperatures only a few degrees above absolute zero, the background temperature of the universe, about -270 degrees Celsius. But a substantial atmosphere could act as insulation, trapping heat through the greenhouse effect and maintaining warmer temperatures at the surface or in the lower atmosphere, even without any external heat source. A rogue planet with a thick hydrogen atmosphere could potentially maintain surface temperatures warm enough for liquid water through atmospheric pressure and greenhouse warming alone. Hydrogen is the lightest and most abundant element in the universe, and large planets can capture and retain massive hydrogen envelopes during formation. The greenhouse effect from a thick hydrogen atmosphere, combined with internal heat radiating from below, could create a temperature profile that allows liquid water to exist at the surface or at some depth within the atmosphere, where pressure and temperature are both suitable. Computer models suggest that a rogue planet several times Earth's mass, with a hydrogen atmosphere perhaps 100 times more massive than Earth's atmosphere, could maintain surface temperatures above the freezing point of water for billions of years, powered only by internal heat. Such a planet would be entirely dark at the surface, no day or night, just eternal darkness. But it would be warm enough for liquid water, and where there's liquid water and a source of energy, life becomes possible. Life on such a world could not depend on photosynthesis, but that's not necessarily a problem. On Earth, entire ecosystems exist in permanent darkness, sustained by chemosynthetic bacteria that extract energy from chemical reactions rather than sunlight. Deep-sea hydrothermal vents host thriving communities where bacteria oxidize hydrogen, sulfide, methane, or hydrogen, using the chemical energy to build organic molecules from carbon dioxide. These chemosynthetic bacteria form the base of food chains that support tube worms, clams, fish, and crustaceans, all living in absolute darkness, kilometers beneath the ocean surface. A rogue planet with liquid water oceans, maintained by internal heat and atmospheric greenhouse warming, could develop similar chemosynthetic ecosystems. Volcanic activity would vent gases like hydrogen, hydrogen sulfide, methane, and carbon dioxide into the water and atmosphere. Bacteria could evolve to extract energy from these chemicals, building organic molecules that could support more complex organisms. The entire biosphere would operate on chemical energy from the planet's interior rather than solar energy, making the planet's life forms independent of any star. Subsurface oceans represent an even more plausible habitat for life on rogue planets. Many worlds in our solar system likely have liquid water oceans beneath ice shells. Europa, Enceladus, possibly Titan, Ganymede, Callisto, Pluto, and other bodies. These oceans are kept liquid by tidal heating from their parent planets, or by internal radioactive heating. A rogue planet with sufficient internal heat and a thick ice shell could maintain a subsurface ocean indefinitely, with the ice providing insulation that prevents the ocean from freezing while protecting it from the harsh radiation and extreme cold of interstellar space. The ice shell on a rogue planet might be very thick, perhaps tens or hundreds of kilometers, creating an insulating layer that traps internal heat far more effectively than any atmosphere. The ocean beneath this ice would be completely dark, protected from the radiation that fills interstellar space, and stable for billions of years. Temperature would be maintained by heat flowing from the rocky mantle below. Hydrothermal vents on the ocean floor would provide chemicals and energy for chemosynthetic life. Such an ocean might be an ideal habitat, more stable than surface oceans on planets orbiting stars where stellar evolution, asteroid impacts, and climate variations create periodic catastrophes. Life in a subsurface ocean on a rogue planet would never know stars exist. The entire biosphere would be confined to the dark ocean, with the ice ceiling above and rocky floor below defining the limits of the habitable universe. Evolution would never produce eyes sensitive to visible light, because no visible light exists. Organisms might instead evolve chemical sensing, pressure sensing, electroreception, or other non-visual senses. Intelligence, if it evolved, would develop without ever seeing stars, planets, or anything beyond the ocean's boundaries. Such a civilization might not even realize that a larger universe exists beyond their world, having no way to detect or observe the space around them through kilometers of ice. Geothermal pockets could create localized habitable zones even on rogue planets without global oceans. Volcanic activity or concentrations of radioactive elements could heat specific regions, melting ice to create underground lakes or pockets of liquid water embedded in ice. These isolated water bodies might be small, perhaps only a few kilometers across, but they could persist for millions of years, long enough for life to evolve and diversify within each pocket. Different pockets might develop different ecosystems in isolation from each other, creating multiple independent evolutionary experiments on a single rogue world. Atmosphere composition would profoundly affect habitability. A rogue planet that retained or captured a hydrogen-helium atmosphere during formation could use that atmosphere's greenhouse effect to maintain warmth. Carbon dioxide, methane, and ammonia are all more effective greenhouse gases than hydrogen and would enhance warming at much lower atmospheric masses. A rogue planet with a thick carbon dioxide atmosphere and substantial internal heat might maintain temperatures warm enough for liquid water with a much thinner atmosphere than a hydrogen-dominated world would need. The size of the rogue planet matters significantly. Larger planets generate more internal heat from radioactive decay simply because they contain more radioactive material. Larger planets can also hold thicker atmospheres through stronger gravity and lose heat more slowly because their surface area to volume ratio is smaller. Heat escapes through the surface, but heat is generated throughout the volume, so larger planets stay warm longer. A rogue super-Earth several times, Earth's mass might remain habitable for far longer than an Earth-mass rogue planet, potentially maintaining surface or subsurface liquid water for tens of billions of years or more. Very small rogue planets, Mars-sized or smaller, would struggle to maintain habitability. They would cool quickly, losing internal heat within a few billion years. Their weak gravity would allow atmospheric escape, making it difficult to maintain the thick atmospheres needed for greenhouse warming. However, even small rogue worlds might maintain subsurface liquid water in deep aquifers or isolated pockets warmed by concentrations of radioactive elements or by residual heat from formation for some period after being ejected from their parent system. The abundance of rogue planets remains uncertain, but some estimates suggest they might outnumber stars. If planets are commonly ejected during the chaotic early phases of planetary system formation, the galaxy might contain billions or even trillions of rogue planets drifting through interstellar space. Most would be cold, dark, and apparently lifeless at their surfaces, but some fraction might maintain subsurface oceans or possess the right combination of size, composition, and atmosphere to support life in hidden biospheres, beneath ice or in dark surface oceans sustained by nothing more than the planet's internal warmth. Detecting life on rogue planets would be extraordinarily challenging. These worlds emit no reflected starlight, making them nearly impossible to detect through traditional astronomical methods. They can only be detected through gravitational microlensing. When a rogue planet passes in front of a distant star from Earth's perspective, its gravity briefly magnifies the star's light, or through direct detection of their infrared emission, the faint heat radiating from their surfaces. Neither method provides information about atmospheres, surface conditions, or potential habitability, let alone biosignatures. Future infrared telescopes might be able to detect the warmest rogue planets and potentially characterize their atmospheres if those atmospheres are thick enough to produce detectable spectral features. Finding methane, carbon dioxide, or other gases in unexpected ratios might hint at biological activity, though distinguishing biological from geological sources would be nearly impossible without additional information. Direct exploration by spacecraft seems impractical, given the vast distances between stars and the difficulty of even locating rogue planets, let alone traveling to them. The evolutionary trajectory of life on rogue planets might differ fundamentally from life on planets orbiting stars. Without the regular day-night cycle that drives circadian rhythms on Earth, organisms would have no reason to evolve time-keeping mechanisms tied to planetary rotation. Without seasons caused by axial tilt and orbital motion, there would be no seasonal cycles, no annual rhythms. Life would exist in an eternal, unchanging environment, at least on timescales shorter than geological epochs, potentially leading to very different evolutionary pressures than life on Earth experiences. The isolation of rogue planets creates another interesting possibility. These worlds might serve as interstellar arcs, carrying life between star systems. If a planet with a biosphere is ejected from its home system, life on that planet doesn't necessarily die. If the planet maintains subsurface oceans, through internal heating, life in those oceans could survive indefinitely, potentially for billions of years, as the planet drifts through the galaxy. Eventually, such a planet might be captured by another star system, or it might pass close to a star that warms the planet temporarily, allowing surface life to revive if it was dormant. This mechanism, planets carrying life between star systems, represents a form of panspermia that could spread life throughout the galaxy. How life could survive on rogue planets demonstrates the resilience and adaptability of biology when provided with even minimal requirements. Liquid water, chemical energy, raw materials, and time. A rogue planet, cut off from all starlight, drifting through the darkness of interstellar space for billions of years, seems like an impossible place for life. Yet internal heat and thick atmospheres, or ice shells, could create hidden habitats where chemosynthetic ecosystems thrive in eternal darkness, where evolution operates unconstrained by day-night or seasonal cycles, where intelligent beings might arise never knowing that stars exist, and where life demonstrates its ultimate independence from sunlight, proving that biology requires not a sun to orbit, but merely the right chemical conditions and energy sources, expanding the definition of habitable environments to include not just planets in stellar habitable zones, but potentially countless dark worlds adrift in the spaces between the stars, each one a potential harbour for life in the vast ocean of the galaxy. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shock waves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Xio, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty.